The learning objectives for this video are to learn how to name alkanes and learn about properties of alkanes. You may find that you actually like learning how to name alkanes. I've always been shocked by how much students like this particular topic. Perhaps it has to do with how orderly it is. There's a series of rules and you just go through every single step and you will get to the right answer. It's a very linear process, but it is detailed. So we have to have a uniform way of naming compounds. And there's an organization called the International Union of Pure and Applied Chemistry, the IUPAC, that has come up with a systematic method of naming all organic compounds. And the name for any compound can be broken up into a locant, which tells us where the substituents and functional groups are, a prefix, which tells us what are the substituents, a parent, which tells us how many carbons the compound has, and then a suffix, which gives us the primary functional group. And in these next slides, I'm going to give you a series of rules for naming alkanes, and then we will practice as we go along. So the rule 1 is that you want to find the longest continuous chain, and this will be used as the parent name. So for example, if we look at this molecule on the left, that chain here has 1, 2, 3, 4, 5, 6, 7, 8 carbons. This chain that I just highlighted in yellow. But there's another chain you could have looked at if I went down here. So if I start here, that would be 1, 2, 3, 4, 5, 6, 7 carbons. So the chain that I circle in green has 7 carbons. The chain that I circle in yellow has 8 carbons. So between those two, I want to choose the one that has more carbons. So my yellow chain is going to be my parent chain. Now I just name that parent chain. And here you have to use your table of memorized names for alkanes. So you have methane, which has 1 carbon, ethane, which has 2, propane, which has 3, and an 8 carbon chain we call octane. So the parent name here is octane. So let's also figure out the longest chain and hence the parent name for the second compound. So this chain here that I'm highlighting in yellow has 1, 2, 3, 4, 5, 6 carbons. But if I look at a different chain, let's see, this chain that has how many carbons? It has 1, 2, 3, 4, 5, 6, 7 carbons. So the longer chain there is the 7 carbon chain, so that will be my parent. Now when you're figuring out which is the longest chain, you want to follow along the chain without picking up your pen on the paper. So what is the name for a 7 carbon chain? That would be heptane. So that satisfies rule number 1. Now rule number 2, we need to number these carbons. And the rule is that you number from the side nearest to the branching. So the branching is where something is hanging off of the chain. So I'm going to redraw this structure. So I said there that the yellow portion is my parent chain. So I'm going to number from the side that gives the branching the lower number. So if I number from the right, 1, 2, 3, 4, 5, 6, 7, 8, this branch here arrives at carbon 4. Now if I numbered the other direction from left to right, 1, 2, 3, 4, 5, 6, 7, 8, that branching would occur at a later number at carbon 5. So the numbering in blue is the numbering that we want. Now let's try this also for the next one. So I'm going to redraw this. And here I said that the longer carbon chain was the 7 carbon chain highlighted in green. So I want to number it so that the branching occurs at the lower possible number. So let's number from this side. So 1, 2, 3, 4, 5, 6, 7. So my branching, looking at something hanging off of the designated parent chain, is at carbon 3. If I number the other direction, 1, 2, 3, 4, 5, 6, 7, well, the branching doesn't arrive until I get to carbon 5. So I want to number as shown in red. Now, using that numbering that we just figured out in the last slide, we want to designate the substituent that's attached to the parent chain. So here we decided that the numbering would go like this: 1, 2, 3, 4, 5, 6, 7, 8. And on this one, we decided the numbering would go like this: 1, 2, 3, 4, 5, 6, 7. Now, what's my parent name for this one? It's octane. For this one, it's heptane. So now I just need to indicate what substituent is at what carbon. So at carbon 4, that's where I have my branching, I have a 2-carbon substituent that's called an ethyl. So then we just include that information in the name. So the name becomes 4-ethyl octane. Now, as a reminder of how to name alkyl substituents, you take the normal name, for example, for a 2-carbon alkane would be ethane, and you remove the ane ending and add YL. So now let's try the next one. So here we have the branching at carbon 3, and at that branching we have 1 carbon. We have a CH3 group, which is called a methyl group. So now we just add that information to the name. So this becomes 3-methyl heptane. Now we're steadily getting more complex here. So rule number 4, if there's more than one substituent, so more than one group hanging off of that main chain, you want to start numbering from the end of the main chain with the nearest substituent, and then you have to indicate the location of each substituent. Also, we want to put the names of the alkyl substituents in alphabetical order. So first of all, can you find the main chain? It's going to be the longest carbon chain. So that will be 1, 2, 3, 4, 5, 6, 7, 8. That will be this chain. 1, 2, 3, 4, 5, 6, 7, 8 carbons. So now we want to number from the end with the nearest substituent. So that would be from the left. So 1, 2, 3, 4, 5, 6, 7, 8. The substituent is closer to the left, the first substituent, so that is how we number. Now let's look at what's attached at carbons 2 and 5. This is a CH3 group, which is called a methyl. This is a CH2CH3 group, which we call an ethyl. Now we just have to assemble it, remembering that we have to put the substituents in alphabetical order. So the whole name becomes 5-ethyl 2-methyl octane. And the E is alphabetically before M, so the ethyl comes before the methyl. Now rule number 5, if 2 or more substituents are on the same carbon, use that number twice and name accordingly. So let's practice with this compound. So first find the longest chain. This is a 6-carbon chain. 1, 2, 3, 4, 5, 6. There is not a longer chain. Now we want to number from the side where we get the branching at the lower possible number. So that would be numbering from the left. So the numbering is going to go 1, 2, 3, 4, 5, 6. Now there are 2 groups on carbon 3. There's this 2-carbon group, which we call an ethyl, and a 1-carbon group, a CH3 group, which we call a methyl. So the ethyl is at 3, as is the methyl. Now we want to assemble all of this together. So first, the parent name is hexane. And I have to remember my alphabetizing. So 3-ethyl 3-methyl hexane is the proper name. Also, you may notice that I have hyphens. The rule for when to use a hyphen is anytime you're moving between a letter and a number in either direction, you use a hyphen. Okay, now let's look at Rule 6 and 7. So Rule 6 says when you have two or more substituents that are identical, indicate that using the prefixes di, tri, tetra, etc. Rule 7 says when there are chains of equal length, choose the chain with the most branching. So let's first find the chain with the most carbons. So let's see, 1, 2, 3, 4, 5, 6, 7. That's a 7-carbon chain. Is there another chain that has more carbons or a chain with an equal number of carbons? So here we've got a 1, 2, 3, 4, 5, 6, 7 carbon chain that I'm circling in green. So we have equal length chains. So to choose between them, we choose the one with more branching. The chain that's yellow has 4 branching points, whereas the chain that's green only has 3 branching points. I will use the chain in yellow. Now I want a number from the end that gives the substituent, the first substituent, the lowest possible number. So that would be numbering from the left. So 1, 2, 3, 4, 5, 6, 7. So there, that first substituent is at carbon 2. If I had numbered from right to left, the first substituent wouldn't have arrived until carbon 3. Now what do I have at these different carbons? I've got a methyl here, a CH3 group, a methyl here, a 1, 2, 3 carbon chain, that's called a propyl, and then a methyl at carbon 5. So rule number 6 says when I have more than one of the same substituent, I use a prefix. So how do I assemble this name all together now? So the parent chain is heptane. And I have 3 methyl groups of carbons 2, 3, and 5. And they're going to alphabetically come before propyl. So this will be 2, 3, 5, trimethyl, 4, propyl, heptane. The final rule, rule number 8, when the first branching occurs at equal distances from the end, start at the difference that will give the lowest number at the first point of difference. So let's first look at the longest carbon chain. That's going to be this one in yellow. That has 1, 2, 3, 4, 5, 6. Now, if you had instead dipped down here, you could also have used that chain. The yellow and green chain are actually identical, and you'll get the same name no matter which one you use. So let's just stick with the chain in yellow. So we want a number from the side that gives the lowest number at the first point of difference. So if I number from the left, 1, 2, 3, 4, 5, 6. I have a substituent at carbons 2, 4, and 5. If I number from the right, 1, 2, 3, 4, 5, 6, I have substituents at 2, 3, and 5. So I want to use the numbering in red because the second substituent would then be at a lower number 3 than if I use the numbering in blue, where the second substituent would be at the higher number 4. So now I just have to put this all together. So the parent name is hexane. That's the longest carbon chain. It's a 6-carbon chain. And then I've got methyls at carbons 2, 3, and 5 because I'm using the red numbering. So then that would be 2, 3, 5, trimethyl hexane. In addition to straight chain alkyl groups, we can get branched alkyl groups. So for example, this would be the normal straight chain 3-carbon alkyl group, which we would call propyl. But you can also have it arranged like this, where there is essentially branching, and this carbon is attached to two other methyls, and we call that an isopropyl group. For butyl, there are three other types of arrangements of the atoms. In this arrangement, we call that isobutyl. This we call sec-butyl, and this tert-butyl. The reason we call this sec-butyl is that this carbon, which is at the point of attachment, is a secondary carbon. We call this tert-butyl because that carbon, which is at the point of attachment, is a tertiary carbon. The squiggly line just means that's where this group is attached to the main chain. There's also a 5-carbon branched alkyl group called neopentyl. So you want to remember these common names for branched alkyl groups. So let's try this example I've drawn. So first you find the longest carbon chain, that's going to be your parent name, and that's the one that I'm circling in yellow. That is a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. So the parent would be called octane. Now you want a number from the end that gives the substituent, the branching at the lowest possible number, which would be right to left. So 1, 2, 3, 4, 5, 6, 7, 8. If I number the other direction, I get a higher number at the branching point. So this group is my substituent. It's one of the branched alkyl groups. Can you find it on this page? So it looks like an upside down Y. So that is called an isopropyl group. So see the squiggly here? That indicates this point of attachment to the main chain. So then the name is 4-isopropyl octane. I'm going to finish up by mentioning some properties of alkanes. So they are sometimes referred to as paraffins because they aren't very reactive with many chemicals. And that's because the backbone carbon atoms in alkanes have achieved their octet of electrons through forming 4 covalent bonds, and these are sigma bonds, which are very stable. Now, that being said, you can burn them. So gasoline is a mixture of alkanes, and when you burn them, it produces carbon dioxide, water, and heat. It is difficult to convert alkanes into other types of organic compounds. However, you can halogenate them, so this is an example of methane being treated with chlorine to form carbon tetrachloride. And that occurs through what's called a radical process. When you look at the melting and boiling points of alkanes, you will see that with the increasing number of carbons here, the melting point and boiling point increase. And the reason for that is that the larger number of carbon atoms gives rise to greater London dispersion forces, also known as van der Waals forces, which are weak intermolecular forces, but they can have a strong cumulative effect. And when you have a larger molecule, there's more chances that these temporary dipoles will form that will be attracted to one another, and that gives the molecule greater stability, which then requires higher heat to melt it or boil it. And that's the end of this video.